gonna give takes until he returns. So yeah, I predict there'll be a small sparse set of heads that matter, and then a MLP that matters naively, it would just be the last one. Plausibly, there'll be like a small handful of neurons that matter that all significantly boost etsy. It's also plausible to me that there's like some polysemantic bullshit which boosts the like direction in MLP space that most boosts, sorry, the direction in MLP activation space that most boosts the etsy token. And it's plausible there's some other bullshit to deal with like dropout or something. In particular, if it is the case that dropout just like works with, yeah, if it's the case that there's just like a single head or like small set of heads that are doing the smeared thing, then if and it's sensitive to whether the first token is there, then that suggests that if the dropout kills the connection from the buy token to the like output token, then the memorization is going to break. The model does not want this, so it's going to have some redundancy, which might look like a backup head. So the thing which I would predict would happen if it's doing some backup-y behavior is that the key heads for memorization would be in like layer 10 or like layer 9. There will be subsequent heads that occur if you ablate the key heads in layer 9 or 10, which attend to the relevant token in like their layer 1 after. And that, so what I meant by polysemantic bullshit in the heads was that you might get, for example, some like arbitrary direction in neuron space that is not aligned with the neuron basis, which gets passed through the GELU, and then at the end of it, you get a somewhat different vector in MLP activation space, and when you directly map that to the logits, it's high in the etsy direction. The thing you described of the most relevant neurons activate on different memorized sequences. Is it memorized sequences that still end in etsy?
No.
Wild.
But
Cool.
Yeah.
In that case, that totally feels like polysemanticity, but in a different way. Where like I could totally imagine that like the log problem etsy by default is like tiny. And you have this neuron which heavily boosts etsy, and it heavily boosts like Adobe or something. But like in most contexts, you're very confident it's either etsy or Adobe, and so that neuron doesn't make that big a difference or something, because there's other things which are boosting etsy. Probably in that case, I would say you haven't found a complete part of the memorization circuit, but I could totally imagine some like binary code where there's 5 memorization neurons, of which any pair activate for any particular string. And this seems like it would just totally work and get you like 5 choose 2 memorized
it's like
strings.
5 bits. It's like 5 bits in the output.
Not quite. So what I'm imagining is if you've got like 5 neurons, each of which strongly boosts, each of which activates for like 2, each neuron activates for 2 memorized strings, then it, so long as each string activates different pairs of neurons, you're pretty happy, because the etsy neuron, the like etsy and Adobe neuron will fire for both Adobe and etsy. But if the other Adobe neuron isn't firing, you'll like boost etsy by 20 and you'll boost Adobe by 10. So you don't really notice.
So it's like polysemantic for, rather than polysemantic for the features, it's polysemantic for the data points.
Yes, I'm mildly unconvinced about the feature versus data point framing, but this doesn't feel super important here. Yeah. Sorry, the thing which I'm trying to disentangle is there's some sparse representation across neurons where like some amount of neurons matter, but it's like 5. And there's some like totally not basis aligned shit where it's just like wildly aligned. Anyway, does that make sense?
Yes.
Cool. So my advanced prediction before I look at the causal scrubbing results is there'll be some small set of heads that matter in like layer 9 or 10. If you ablate them, there'll be some backup heads that take over in the like next layer or the layer after. And there will be some fairly sparse set of neurons that matter a lot in layer 10 or 11, where if you delete some of the neurons, if you delete the neurons that aren't in the like top 1% of neural activations, it's kind of fine, is my prediction. Cool. How wrong am I?
So we tried running causal scrubbing on just one example, and we could recover 80% of the loss with MLP11 and these 4 heads.
Okay.
Yeah, but this is just one example, so we don't think this will generalize well. And then I just
But yeah. What do the attention patterns of the heads look like?
I think we looked at some, but they did not look very convincing. Let me check if I can find those.
They attend strongly to like the first position. I remember looking at head 9 or head 8.
Interesting. Another concrete experiment idea. Have you tried resampling individually specific tokens in the sequence?
No, we haven't tried that.
Cool. Seems worth a shot. Just like replace with some random arbitrary token between, I don't know, in token index 300 and token index 500. Fairly common tokens.
When you say resampling tokens randomly at different sequence positions, does it mean after we provide the prompt which triggers memorization, or
sorry, what I mean is, so you've got this sequence by clicking accept blah blah blah, and what you do is you just have, say there's 8 tokens in the sequence, you do 8 like 8 times 10 runs, and for the first set of 10 runs you just randomly choose 10 alternatives for the first token, sub each of them in turn and look at the logit difference. Then for the second set, you look at the second token, iterate over 10 runs, etc. And this is a dumb way to just test which like tokens matter. And it wouldn't massively surprise me if it's really sensitive to like a specific token and not sensitive to the rest. So I would actually have predicted it'll be really sensitive to like the 4th token rather than the 1st or something, because it seems like you might want something that's like taking into account whether the first handful of things matter or something, if that made sense.
Yeah.
These are for path patching.
Oh.
And sorry, these are attention patterns, or
Yeah.
Cool. Wild. Oh, so the fact that it's looking at register is interesting. But cool. Okay, this feels like evidence for a mix of the smearing hypothesis. And sorry, this is direct path patching to MLP11?
Yeah.
Or,
Cool.
So
logits, yeah.
Logits, sure. Cool, makes sense. Okay, I'm happy to move on.
Yeah. And yeah, so after like finding MLP11, I just tried to iterate over that node and find out like which nodes affect MLP11 directly. And that was again mostly MLP10 and some other heads here and there, which weren't very significant.
Makes sense.
Yeah, and when I continue to do that for MLP10, it's again MLP9. I see there are some heads getting active, but I did not pursue the heads in this kind of plot because the
Mhm.
total effect size of these heads is kind of very less than
Sure.
the overall effect
Mhm.
size. So
Mhm.
it's kind of insignificant. And
Mhm.
then I tried so today I started with path patching with like multiple examples, and
Mhm.
the plot kind of changes.
What
And it's
exactly do you mean by path patching here?
Like looking at the impact of all the nodes on
Mhm.
the final token prediction.
Mhm.
Yeah, and I'm
Mhm.
doing this simultaneously for 10 examples over here,
Mhm.
10 memorized examples, and some examples that we have perturbed manually to
Mhm.
kind of get the perturbed inputs. So yeah, so here the effect is kind of mostly in MLP, but then
Mhm.
this would be dominated by examples that have by default very high logit differences.
Mhm.
So this does not look very representative, but yeah. So
Mhm.
we're currently, so this was plot that I generated, I think, an hour
Mhm.
ago. So we
Makes
are
sense.
currently
A
exploring
really
this.
dumb thing you could do is just look at the median logit diff.
Okay.
Looking at the like nth percentile also seems reasonable.
Yeah. Yeah. And I think Tessa mentioned this. So there are some neurons that fired for multiple
Mhm.
memorized sequences in MLP11, 584 and 2123 are kind of those
Mhm.
top two neurons. So
Mhm.
we're trying to do some experiments with specific neurons as well. Yeah,
Mhm.
I mean, that's all we have for now.
Mhm.
Oh, okay. And there is this thing. I think Tessa can explain this.
Oh, so this is a linear probe trained on
Mhm.
our data set of like 200 memorized versus specifically not memorized sequences on the output of the hidden dim for each layer. And we see that the model by layer 10 can
Mhm.
distinguish with 75% accuracy the memorized versus not memorized samples. So I don't know where to necessarily, like, I don't know how the model knows by, like, I don't know how to figure out how the model knows by layer 10 with this confidence what is going to be memorized versus not memorized.
What exactly is the probing data set here?
So it is this data set that I collected manually from open web text of a sequence that elicits like a key value type of memorized sequence. And then I perturbed the memorized sequence with random like word switches until it no longer output that like sequence of like deterministic values. So I tried to use like the minimum edit and semantic distance to perturb the sequence.
Interesting. Have you tried doing it with just like arbitrary token, just like single token switching?
Well, so we could do that, but like some of these are pretty robust actually. So like, yeah, I suppose in expectation.
I'm just interested in what happens. It wouldn't surprise me if the answer is it totally fails. But
yeah, I'll definitely try that.
Makes sense. Yeah, I am mildly surprised it gets pretty good accuracy so early. And this is a single memorized prompt. Or
no, I think there are 70 memorized prompts.
Oh, what?
Yeah. So the data set has 70 examples, right?
Yeah. 70 positive and then 70 negative that I got via perturbations. And there's no overlap among the positive examples. So there's no like subsequences of other memorized that the model could be like using to cheat. with this linear probe.
Yeah. We're not sure if 70 examples is enough for a linear prompt to be very informative, but
so yeah. So one important test you should do is randomize the labels and then check.
Okay.
Since it's really easy with probing to just give it a bullshit task.
That's a good idea.
But yeah, I'm surprised it's so good at it. What exactly do you mean when you say test accuracy here? Like, what was the test set?
Oh, so I took the 70, I divided it up into 75% training for the linear probe and 25% testing.
Oh, what? So it's just like detecting memorized sequences.
Oh, it knows. It knows.
It's detecting the fact that it has memorized.
Well, the features that distinguish memorized versus not memorized are linearly separable. So
wild. Huh. I mean, yeah. Okay, this is surprising, but not like super interesting to me as data, because it feels like there could be a bunch of boring explanations, like it's detecting coherent English or something.
no, but all the other ones, the negative samples are really similar. They're just like slight perturbations.
Oh, okay.
Do you want to see the data set? It's like kind of like, it's just
sure.
Okay, let me share my screen.
I'll stop sharing.
And to check, hidden layer 0 means the residual at the start of layer 0. Hidden layer 12 means the residual at the end of layer 12.
Yeah.
Like the start of layer 12, so the final residual string.
Okay, can you guys kind of see the...
Yep.
So this is just like the first line is the positive sample, and then the third line is the negative sample. And so we just have a bunch.
Gotcha.
So there might be a good example why, but I tried to pick high probability phrases, but it's all dependent upon my ability to generate high probability phrases, high likelihood phrases.
Oh, I mean, have you just run GPT-2 on the new phrases and checked if there's like a obvious difference in like per token loss?
Loss?
Like per token log prob.
Oh, I haven't done that, but that makes sense.
Yeah, I know. I don't actually think the linear probe is like super interesting.
Okay.
Because I'm much more interested in how the model memorizes a specific sequence than like whether there is a general I have memorized right now neuron, because that doesn't feel like an interesting part of the puzzle to me, or like not uninteresting but like less interesting. Yeah, so what are my high level tips? I don't think I feel massively surprised by things. I find it mildly interesting that it looks like the MLP, that like the key input to MLP 11 is like MLP 10, and the key input to MLP 10 is like MLP 9, rather than heads. Like that feels interesting to me. Though, oh yeah, so another hypothesis I had is that, so have you come across the Solu paper? Random anthropic paper where we were looking at activations that seem to make neurons a bit more interpretable. And one thing we found in there was these re-tokenization neurons, which took words that had like, I don't know, the word stragglers is split into st-rag-glers. And we found a neuron that fired on like st to predict rag only when it was the word stragglers, not in other instances of st, and things like that. And so what we thought was happening was that the model had some like, this is stragglers direction that it was, and this activated some neuron whose job it was to like convert this is stragglers neuron, is stragglers direction to like subsequent things. So like actually taking the specific actions, rag and glur. Does that make sense? Like there is a single task to figure out as the word stragglers. There are 3 actions you're supposed to take: predict stir, predict rag, predict glurs. And there was like a neuron for each of the actions, which converted the like, this is the word stragglers concept into the 3 relevant actions. Which you can kind of think of as analogous to like motor neurons that like, let me move my fingers. Once I've decided, like move hand upwards or something. And
how would they be relevant for us? Because we need to find like some neurons first, or would they be helpful in finding neurons for memorization or some sparse patterns in MLP11 or something?
So the reason I think this is relevant is that one prediction I would make, so 2 possible ways you could implement memorization. So you've got this like memorized 12 token string that gets activated by the first 8 tokens, say. In this case, I would, 2 ways you could do it. You could have a separate memorization circuit for each of token 9, 10, 11, 12, each of which has their own neurons and their own attention heads. Or you could have like a memorization neuron in layer 10, and then layer 11 attention heads, which move that to subsequent things, and then neurons which activate if like that head picked up on the I have memorized feature, and a neuron which activates if like the current token is rag and the look at memorized head noticed stragglers. And then a separate neuron branch activates on lurs and does that, etc. Does that make sense?
Yeah, it's like an analogy between a word and a memorized sequence.
Yes. But the distinction I'm trying to make is in the hypothesis where there's a kind of re-tokenization circuit, there should be some like single token where the model has clearly figured out that it's memorized earlier, and then some separate bits, and then like some key heads that move that to later tokens in the sequence and convert that to the specific output tokens. In the separate circuit per token hypothesis, you're not going to find any bottlenecks like that. Dropout makes the story messier, but I expect there's still something like this going on.
Yes, that would be very interesting. So the head was copying the re-tokenization bit to the...
Yes.
Okay.
And like one concrete thing you could do to test this is like ablate the residuals for like each token in the memorized string, like ablate the residual stream at like layer K and iterate over like all layers K and like all token positions P. And one prediction this would make is that there's like some token position where ablating it later matters a lot more than ablating it earlier or something. I'm like not 100% confident in this, because I could totally imagine there's a separate I have stopped memorizing circuit which checks whether there's any break in the chain. And the way I try to disentangle the two is by like resample ablating the input tokens at every point in the memorized string and see what that changes. Does that make sense?
Yeah.
Yeah,
So,
so there's, yeah, do you want to repeat back to me what the experiment ideas are and why they matter?
yeah, so one is like to ablate all the sequence positions. So when you say that to ablate all the sequence positions across all the layers, do you mean that should I ablate them? Should I ablate all the sequence positions together or each
No.
sequence position one at a time?
For every pair of sequence position and layer, ablate that layer at that position.
Got it. Yeah.
And it like wouldn't massively surprise me if the answer is it's not very sparse, or like, oh, it's super, or like, oh, if you ablate anything around the start, everything totally breaks. The thing which would feel exciting to me is if like in the second half of the sequence, there's like one bit later on that really matters or something. Though I don't expect it to be perfectly clean because I expect the model is going to start memorizing early in the string, but it's not going to get to the point where it's overwhelmingly memorized.
Right.
Does that make sense?
Yeah.
And it's going to want some robustness.
Yeah. So I think we have first is to try median logit difference. Second is
yes. Median logit difference is low priority.
Okay. Yeah. And
so it sounds pretty easy.
Yeah. One is related to Solu paper, like trying out what they did to see if we have some analogous behaviors.
No, I'm not proposing do what the Solu paper did, because what the Solu paper did was just look at mech activated dataset examples.
I mean, using Solu instead of Solu is an activation function, right?
No. I am not suggesting that you pivot to looking at a model trained with Solu. I was purely suggesting their glancing at their experimental results as like an interesting case study. Let me just send you a link to the relevant bit of the paper. Yep, here's a link to the relevant section. I would just like go skim that section, and the intention here was a high level. This is a thing that I predict might be happening. If you can show that this is happening, that feels exciting to me. And one prediction I make if this is happening is that there will be late layer MLPs that matter on the subsequent tokens of the string. And the way that these matter is via some heads that are looking at some specific token in the middle of the memorized sequence, where the model has calculated some is memorized on this specific string feature that is being used later on.
So Kushal, we are going to ablate the residual stream, right?
Yes. Yeah. The seq layer pair ablation was designed to test this. Though I think it's a pretty noisy thing. But yeah. Another thing you could do to test this is to for each like pair of token positions, resample ablate all attention between that pair of positions. So the intention behind this is like, if there is some kind of sparsity where there's some this actually tests two separate hypotheses at the same time, which is a bit annoying. The two things this tests is the model sensitive to whether the entire memorized string is there. And secondly, is the model sensitive? Is the model doing some re-tokenization? If it's doing re-tokenization, I predict there will be like some MLP layers where things start mattering for like a pair of positions later on. And I predict that like there will be some specific token position that really matters to like all later things.
Kushal, don't worry, we're recording too.
Okay.
You don't have to worry.
Yeah, I mean, writing things down is useful.
Yeah.
Yes. And yeah. Please have the resample tokens in the sequence experiment idea on there, because I think that's high value and easy. Yeah. All right, so I guess zooming out, the things which feel exciting to me here are one, this is clearly a neuron-based task, and I'm excited about getting more data in neuron interpretability and specific things I'm interested in figuring out. Is it the case that there's some specific set of neurons that matter a lot here? Or like, if there is like a clear direction at MLP space that matters a lot, where the neurons that directly boost the logits are the interesting thing to check here. Is it the case that the neurons are like, is it the case that these neurons are monosemantic? Sorry, I'm not referring to neurons. I'm referring to the memorized ETSI sequence feature. Is it the case that this feature is represented by a single neuron, by a small, sparse set of neurons, potentially with some overlap with other memorized strings in some binary code? If either of these two is true, I'm like very interested, and that feels like the most exciting outcome of this project to me. The third would be some like thing that you don't really know how to interpret, which is kind of smeared across a bunch of neurons, where there's no specific neurons, where if you ablate those, things significantly change. One observation is that you might not want to be using the logit difference metric, and you might instead want to be using like just the ETSI logit, because it's plausible to me there's two circuits. There's predict hour because of some specific circuit to do with grammar, and then there's predict ETSI for some specific circuit to do with memorization. And I don't care about the hour circuit, I care about the ETSI circuit. So I'd try repeating your results without taking logit difference, but just looking purely at the ETSI logits.
Are we allowed to compare logits directly, or do we have to compare the softmax scores?
I'm personally fine with comparing logits directly, because it's just, so it is unprincipled in the sense of maybe something just boosts like all ETSI tokens, like all tokens, including ETSI or something. One thing you could try doing is like have have the kind of top 20 tokens and look at the average of those logits as your baseline, or like have your 70 memorized strings and look at the average of all next tokens in the memorized strings or something. Nah, the second one's going to be messy. I would just like have several metrics and plot the graphs for all of the metrics, because I don't think that's like that much more complicated.
Mm-hmm.
And if you notice significantly cleaner graphs for one metric than the others, that's interesting.
We actually saw cleaner graphs for when we compared direct logit values across different examples. So like if, for example, in case of ETSI, by clicking and by choosing, by just doing that variation, there were some heads getting activated, but then we decided that because we are comparing different probability distributions, we should not compare absolute logit values. And if we do with softmax, the graph is very bad. It's very sparse. Yeah.
Wait, why is that bad? That sounds good.
No, sorry, not sparse. It's entirely concentrated on the MLP. Yeah.
Yeah, makes sense. All right, so let me check other takes. So
just to confirm, you still think that like comparing direct logit values across different examples is fine?
No, sorry. So I'm specifically saying look at direct logit attribution for like specific activations or neurons.
Okay.
I'm not saying look at the entire absolute logit, that entire absolute logit. I'm saying look at the marginal effect on the logit from different components.
Yeah,
which to me feels much more principled.
Okay, so no, when we are doing like path patching experiments, so the path patching experiments currently, we have plotted like the logit differences. Can we do with logit values?
Yes, so long as you're looking at the so there's two things here. There's the difference, you're looking at the difference between the etsy and the hour logits, and you're looking at the difference in difference between like the patch and the unpatch.
Right.
Looking at the difference in the etsy logit between patch and unpatched feels okay by me.
Okay.
Looking at just the etsy logit without doing any differences feels sketchy. Looking at the effect of a neuron on the etsy logit feels okay by me.
No, what did you say was sketchy?
Thing that's sketchy is looking at the absolute etsy logit without taking any differences at all.
No, so we'll take difference between like the baseline and the patched and unpatched.
Yes, that is fine.
Okay. Yeah.
Does that make sense?
Yeah.
Great. And yeah, so yeah, interesting output one. What exactly are the neuron representations? Are they monosemantic? Are they sparse? Are they diffuse? In a world where they're sparse, something that feels interesting to me is whether they are sparse all in the same layer or they're sparse across layers in terms of the direct effect on the outputs. Because of the residual stream, if a neuron, if like the model is doing if the model only cares about 5 neurons, it doesn't strictly need to have all 5 neurons in the same layer. It could have like 3 neurons in layer 10, 2 in layer 11. This is different from having 3 neurons in layer 10, which compose with 2 neurons in layer 11, because all 5 neurons act by their direct effect on the logits. The concrete way I would test this is for every neuron, you can look at its direct logit attribution. Does that statement make sense?
Yeah.
Like you take the neuron activation.
In all the layers, right? Or in just the last layers where it's important.
You can look at this for every neuron in every layer if you really want to. I predict it's not going to matter, but it might matter. And yes, so for like all num layers times num MLPs, neurons, which in this case is like 36,000 or something, you get a scalar, which is the direct effect on the etsy logits, which is the like neuron output vector times the unembed for the etsy thing, times the neuron activation.
Right.
And then you want to take that. You might also want to do this for logit difference between etsy and hour. So just get like 2 sets of 36,000 scalars and then just like sort by that, see how sparse it is. And yeah. If you think it is the case that in the like final layer or layer or two, there's only like some sparse set of neurons that matter, you can try causal scrubbing those. Though this is like not super legit because it's plausible that, say, neurons in layer 10 matter because they compose with layer 11. And yeah, I would be super interested if there's some kind of sparse coding here where it's, I don't know, doing some binary code where it's got 5 neurons and pairs of neurons encode for different tokens. All right. Did all that make sense?
Yeah.
Awesome.
Just one question.
Should...
So
yeah, go for it.
Yeah. So when we are looking at different examples, like how should we differentiate? Because when I'm looking at different examples right now, I'm just taking the average of the difference or whatever metric that I'm getting. Does it make sense to do it that way or do it individually for different examples?
I would favor doing it individually. Just like make like 10 graphs and briefly look at all of them. If it turns out to be the case that, the graphs look very different, then I'd maybe try averaging or looking at the median or something. If you're specifically trying to study individual neurons rather than an entire MLP layer, you emphatically do not want to be averaging because specific neurons are going to differ between different things. But yeah. All right, I should head on to the next group. Do you mind if I briefly ask for some feedback on like what was most useful in this call? If anything.
Yeah, I think all the ideas were pretty cool. And the explanations for some of the things that we saw, I found that pretty useful, like for the linear probes thing. Yeah, I think the experiments that the hypothesis and the experiments you suggested make sense. Yeah, I'm not sure how many of these we'll be able to complete before the end of this week, because this is kind of our last week. But yeah, we'll try to prioritize and do some of
Thanks. Yeah. Just to briefly summarize, high priority project 1, resample tokens and just like try to check how important each individual thing is for memorization. Highest priority 2, look at the direct attribution of different logits and see how much there's like a sparse set that matters versus like everything matters. And including for the like first properly memorized token and like subsequent properly memorized tokens. And finally, try to check for whether there's some re-tokenization happening, where resampling individual residual streams is one idea for that. And another might just be causal scrubbing via the MLP layers on like late memorized tokens. Cool. I should head. Yeah, good luck. Excited to see what comes out of this.